Good day, everybody. How are you all? I hope you are doing great. So, we will talk about probability today. I'll share my computer screen with you. So, this is on probability. First section is on terminology. So, probability is a measure that is associated with how certain we are of outcomes of a particular experiment or activity. So probability is the chance or likelihood of a certain event occurring, such as when we toss a coin, what is the probability of getting a head or the probability of getting a tail? An experiment is a planned operation carried out under controlled conditions. If the result is not predetermined, then the experiment is said to be a chance experiment. For example, when I toss a coin, I do not know for sure whether I will get the head face up or the tail face up. So this is an example of a chance experiment. Chance means you can get any of the two faces up in this case. Flipping one fair coin twice is an example of an experiment. Result of an experiment is called an outcome. Okay, outcome is the result of an experiment. The sample space of an experiment is set of all possible outcomes. The upper letter S is used to denote the sample space. For example, if you flip one fair coin, sample space consists of a head and tail, where H is equal to heads and T is equal to 10. Tail, notice the sample space is written with a special kind of parenthesis or bracket. An event is any combination of outcomes. Uppercase letters like A and B represent events. For example, if the experiment is to flip one fair coin, event A might be getting at most one head. The probability of an event A is written as capital P in parenthesis A. The probability of any outcome is the long-term relative frequency of that outcome. For example, when we toss a coin for a number of times, we know in the long run or in the long term, the relative frequency or probability of getting a head is zero point 0.5. But if we toss a coin 10 times, we do not expect to get 5 heads and 5 tails. However, if we increase the number of times we toss the coin, such as to 5,000 times, we might get almost close to 50% head and 50% tail. Probabilities are between 0 and 1 inclusive. That is, 0 and 1 are and all numbers between these values. When the probability of an event P of A is equal to 0, means that A can never happen. When probability of A is equal to 1, means the event A always happens. When probability of A is 0.5, means that the event A is likely to occur or not to occur. Such as, we know in the long run, the probability of head is 0.5. Either it will happen and that probability is 0.5 or it will not happen. Equally likely means each outcome of an experiment occurs with equal probability. If you toss a fair coin, a head, written by capital H, and a tail, T, are equally likely to occur. So we know in the long run, again, long run means number of tosses is very large, then the probability of head is 50%, probability of tail is also 50%. Remember, 50% in decimal form can be written as 0.5. Similarly, probability of head is 0.5, probability of tail is also 0.5. To calculate the probability of an event A when all the outcomes in the sample space are equally likely, count the number of outcomes for the event A and divide the total number of outcomes in the sample space. So, suppose you toss a coin 5,000 times. So total number of outcomes in the sample space is 5,000, right? Suppose out of that you get so out of 5,000 stars, suppose you get 2450 number of heads. So probability of head in that case will be 2450 number of times head occurs divided by the total number of outcomes, which is you toss the coin 5,000. So it is 2450 divided by 5,000, and it will be expressed as a decimal, which with my calculator is 2450 divided by 5,000 is equal to 0.49. Okay. For example, if you toss a fair dime and a fair nickel, the sample space is HH, TH, HT, and TT. So you're tossing a fair dime and a fair nickel at the same time. HH means both of the dime and the nickel lands on the surface with the head face up. That's why HH. TH means the dime lands 10 face up, tail face up, and the nickel lands with the H face up. HT means the dime with the head face up, nickel with the tail face up. And TT means both land with the tail face up, where T is equal to tails and H is equal to heads. For the sample space has four outcomes. Let A is equal to getting one head. So one head appears in two times, TH and HT. So it is 2 out of 4, because why divide by 4? 4 is the total number of outcomes or results in the sample space. And out of those 4, only twice head appears only once. So probability of a head is 2 out of 4 or 0.5. An important characteristic of probability experiments is known as the law of large numbers, which states that as the number of repetitions of an experiment is increased, the relative frequency obtained in the experiment tends to become closer and closer to the theoretical probability. What does it mean? So, suppose you toss the coin 100 times. Do not expect to get 50 heads and 50 tails. On the other hand, if you toss the coin 5,000 times, now 5,000 is a large number. You're tossing the coin 5,000. You can expect to get number of heads close to 2,500 and number of tails also close to 2,500. Okay. So in that case, probability of head will approach the theoretical probability of 2,500 divided by 5,000, which is 0.5. Even though the outcomes do not happen according to any set of pattern or order, overall, the long-term observed relative frequency will approach the theoretical probability. The word empirical is often used of the word instead of the word observed. Empirical again means observed. So in the long run, the observed probability of getting ahead, provided you toss the coin many, many times, such as 5,000 times, the probability of head will approach the theoretical probability. The observed probability will approach the theoretical probability of getting a head, which is 0.5. Odd event, an outcome is it the event A or B. If the outcome is in A or is in B or in both A and B. For example, let A represent the set of numbers 1, 2, 3, 4, 5, and B represent the number 4, 5, 6, 7, 8. So probability of A or B is 1, 2, then 3, 4, and 5 is repeated both in A and B. Notice in A or B, we represent the numbers 4 and 5 only once, not 10, twice. So A or B consist of 1, 2, 3, 4, 5 only appears once, both of them, and then 6, 7, 8. Notice then 4 and 5 are not listed twice. And what is an AND event? So that was an OR event. An outcome is in the event A or B if the outcome is in A or is in B or in both A and B. Okay. What about AND? An outcome is in the event A and B if the outcome is in both A and B at the same time. And we know 4 and 5 are repeated both in A and B. So for example, let A be 1, 2, 3, 4, 5 and B, 4, 5, 6, 7, 8. So what is common between them, which is A and B, is 4 and 5. The complement of event A is denoted by A with a comma or like an apostrophe, one single one, and it is read as A prime. A prime is the opposite of A. A prime consists of all outcomes that are not in A. So probability of A plus probability of A prime or not A is equal to 1. So let sample space be 1, 2, 3, 4, 5, 6, and let A is equal to 1, 2, 3, 4. What is A prime? Which is not A is 5 and 6. A consists of the set of 4 events, 1, 2, 3, 4, 4 outcomes. And what is not A, then because A is part of that sample space, is 5 and 6, A prime or not A. The conditional probability of A given B is written as PA. If that is not divided by B, it is PA given B has occurred. Okay, so that vertical line means given. And given, anything after the given has first occurred. So in this case, the event B has occurred first and then A has happened. If probability of A given B is the probability that the event A will occur, given that the event B has already occurred. A conditional reduces the sample space. We calculate the probability of A from the reduced sample space B. The formula to calculate probability of A given B is probability of A given B is probability of A and B, which is common to both A and B, divided by probability of B. Why? Because B has happened first, so probability of B is in the denominator, and in the numerator, the common part between A and B, which is probability of A and B, where PB is probability of B is greater than 0. Flip 2 coins. This is an experiment. The sample space are head, 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 tail, tail, head, and tail, tail, where T is equal to tails and H is equal to heads. The outcomes are H, 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 T, T, H, and T, T. The outcomes H, T, and T, H are different. The HT means the first coin showed heads and the second coin showed tails. TH means the first coin showed tails and the second coin showed heads. Let A is equal to the event of getting at most one tail. At most, maximum value is 1. At most, one tail means 0 or 1. Find probability of A. Okay. Let B is equal to the event of getting all tails. Find the probability of B. And that's only 1. Okay. At most, one tail means either 0 tail or one tail. And that is at most one tail means one tail or both tails. Okay. That is HT, TH, and TT. No, it cannot be TT because at most one means only tail is either 0 or 1. 0 or 1 is in HH, no tail, HT, one tail, TH, one tail. So it is 3 out of 4. Okay. Let B be the event of getting all tails, that is TT. It is 1 out of 4. Let D is the event of getting more than one tail. More than one tail is only happening once, 1 out of 4. Okay. Let E is the event of getting head on the first roll, and that is 2 out of 4. Okay. You get either a head or tail on the second roll. Let F is the event of getting one tail in 2 flips. Getting at least one tail means 1 or more in 2 flips. 1 or more. That is in HT, TH, and TT, which is 3 out of 4. Okay. In a bag, there are 6 red marbles and 4 green marbles. So 6 plus 4 is 10. The red marbles are labeled like this, 1, 2, 3, 4, 5, and 6. The green marbles are marked with 1, 2, 3, and 4. R is equal to a red marble, green is equal to a green marble, G is equal to a green marble, O is equal to odd numbered marble. marble. The sample space is R1, R2, R3, R4, R5, R6, and then G1, G2, and G3, and G4. So there are 10 outcomes in the sample space. What is G and O? What is the probability of G and O? Okay. G and O means a green marble and an odd number marble. G and O. So it will be G1 and G3. Okay, more problems. Independent and mutually exclusive event. Two events A and B are independent if the knowledge that one occurred does not affect the chance of the other happens. Okay. For example, the outcomes of two rolls of fair die are independent events. The outcome of the first roll does not change the probability of outcome of the second roll. They're independent. So the probability of an event happening does not influence the probability of the other event happening. Two events are independent if the following are true. Probability of A given B is equal to probability of A, and probability of B given A is equal to probability of B. Okay. So probability of B given A is equal to probability of A and B divided by probability of A. Okay, probability of A and B, if the events are independent, then probability of A and B, since they're not happening together, is probability of A multiplied by probability of B. To show two events are independent, you just show only one of the above conditions. If two events are not independent, then we say they're dependent. If it is not known whether A and B are dependent or independent or dependent, assume they're dependent unless you can show otherwise. Let event A is equal to learning Spanish. Let event B is equal to learning German. Then A and B, learning Spanish and German. Suppose probability of A is 0.4, probability of B is 0.2, and A and B is 0.08. Are the events independent? So to prove, we have to show the probability of A given a B is equal to probability of A. So what is the probability of A given a B? Okay, A given a B is equal to probability of A and B divided by probability of B. So probability of A and B is given as 0.08. Divide that by probability of B, which is 0.2. And the answer is 0.4. And probability of A is indeed equal to 0.4. So probability of A given a B is equal to probability of A. That means these events A and B are independent. Why they're independent? Because the occurrence of B does not influence the probability of A. Okay. So what did I do to do probability of A given a B? I use the formula of probability of A given a B, which is probability of A and B divided by probability of B. So probability of A and B is 0.08, that is in the numerator, divided by probability of B, which is 0.2. Okay, and the answer is 0.4, which is equal to probability of A. Hence, A and B are independent because the probability of A is not influenced by happening of the event B. Sampling may be done with replacement or without replacement. With replacement, if each member of a population is replaced after it is picked, then that number has possibility of being chosen more than once. When sampling is done with replacement, the events are considered to be independent, meaning the result of the first pick will not change the probabilities of the second pick. Such as, think about the pack of a card, okay? So it is well shuffled. So probability of getting a red, we pick one card, getting a red is what? 26 out of 52. So we draw a card, look at its color, and replace it back. Okay. Again, and then we shuffle it again and draw another card. What is the probability of getting a red in the second draw? It will be still 26 out of 52. Since the first card we took out, we replaced it back, reshuffled, and again drew a card. So this is an independent event, okay? Without replacement. Think for a minute. So you have a pack of well-shuffled cards. You have 52 cards. What is the probability of getting a red in the first draw? Is 26 out of 52. Now suppose you do not replace the card that you have drawn. So what has happened now? Total number of cards has now been reduced from 52 to 51 left in the pack. And from that, you are drawing a card. You don't know what color you got. If you have gotten a red card in the first draw, okay, and did not replace it, now you have 25 red cards in the pack, in the left in the pack, and out of that you have a total of 51 cards. So 25 red cards out of 51. That will be the probability of drawing a red in the second chance, provided we got a red card in the first draw and did not replace it back. So you can see the probability is changing from with and without replacement. When sampling is done without replacement, then the events are considered to be dependent or not independent. Why? Because whether we got a red in the first draw will influence the probability of getting a red in the second draw, provided we got a red in the first draw. If we didn't get a red in the first draw, still the probability of drawing a red card in the second draw will also be affected, because if we did not get a red card, now we have 26 red cards left in the pack. 26, but the denominator is now going to change to 51 because we took out a black card and did not replace it back. You have a fair, well-shuffled deck of 52 cards. It consists of 4 suites. The suites are clubs, diamonds, hearts, and spades. There are 13 cards in each suite. Okay. These cards are picked at random. Suppose you can draw the pick. Suppose you know that the pack cards are Q of and the picked cards. Okay, 3 cards you are drawing. So you suppose you draw the picked cards are Q of spades, K of hearts, and Q of spades. Can you decide if sampling was with or without replacement? Okay. 3 cards are picked at random. Because we did not tell exactly whether we replaced it or not, those 3 cards. Suppose you know that the part B, suppose you know the picked cards are Q of spades, K of hearts, and J of spades. Can you decide the sampling was with or without replacement? Well, that has to be specified in each case. So we do not know for sure whether sampling was done with or without replacement. So draw 2 cards from a standard 52 card pack deck with replacement. Find the probability of drawing at least 1 black card. Okay, at least 1 black card. You are drawing 2 cards. Okay, and you are doing replacement. Okay, so at least 1 black card means you can get 0 black card, you can get or 1 black card. The probability of getting a 0 black card, no black card at all, is you're getting red, which is 26 out of 52. Okay. And if you got 1 black card and and the remaining 1 black card, okay, the probability of getting that is 1 out of uh, 26. Okay. And then you can get both of them back cards. Okay. So then that will be each time the probability will be 26 out of 52. A and B are mutually exclusive events if they cannot occur at the same time. This means that A and B do not share any outcomes and probability of A and B is equal to 0. It is not known whether A and B are mutually exclusive. Assume they're not until you can show. If you do not know whether they're mutually exclusive, assume they're not until you can show otherwise. A student goes to the library, let events B equal to the student checks out a book and D is equal to the event student checks out a DVD, let probability of B is equal to 0.4, probability of D equal to 0.3, probability of B and D equal to 0.2. Probability of B given D has occurred, so it is probability of B and D divided by probability of D. So B and D is 0.2 divided by probability of D, which is also 0.3. So it is 0.2 divided by 0.3, 0.2 divided by 0.3, which is 0.67. How about probability of D given B? So it is probability of D and B, which is same as B and D, which is 0.2 divided by probability of B. So 0.2 divided by 0.4, which is 0.5. Okay. What is probability of B given D? It was probability of B 0.4. No, sorry, it is probability of B and D, which is 0.2 divided by divided by probability of D. 0.2 divided by 0.3 is 0.67, and that is not equal to probability of B, which is 0.4. Since probability of B given D is not equal to probability of B, then the events B and D are not independent. Let's try probability of D given a B. It is probability of D divided by probability of D and B. Now, probability of D is 0.3. D and B together is 0.2, sorry. D and B. So, probability of D and B divided by probability of B. So, D and B is 0.2. You divide that by probability of B, which is 0.4, which is 0.5. Now, probability of D by itself is 0.3. So probability of D given a B is not equal to probability of D. Therefore, these events are not independent. Okay. Two basic rules of probability. Remember the rule, probability of A given a B is equal to probability of A and B divided by probability of B. If A and B are two events defined on a sample space, then probability of A and B is equal to probability of A given a B multiplied by probability of B. If A and B are independent, then probability of A given a B is equal to probability of A. So probability of A and B is equal to probability of A given a B multiplied by probability of B becomes probability of A and B is equal to probability of A times probability of B when they are independent. Okay. If A and B are defined in a sample space, then probability of A or B is probability of A plus probability of B minus probability of A and B. If A and B are mutually exclusive, then probability of A and B equal to 0. Then probability of A or B is equal to probability of A plus probability of B minus 0. So it becomes probability of A plus probability of B. A school has 200 senior, of whom 140 will be going to the college next year. 40 will be going directly to work. Okay. So the remainder are taking a gap year. 50 of the seniors going to college play sports. 30 of the seniors going directly to workplace sports. 5 of the seniors taking a gap year play sports. What is the previous taking a gap year? So from all this information, um, you can find the information. Please check out my YouTube video link in order to find the answer to this question, okay? Next one, a student goes to the library. Let B is equal to the student checks out a book. D is equal to the student check out a DVD. Suppose probability of book is 0.4, probability of DVD is 0.3, and DVD given B is 0.5. Prime probability of B and D. B and D. So that will be equal to probability of D given B multiplied by probability of B. So 0.5 multiplied by 0.4 is 0.2. And B or D will be probability of B 0.4 plus probability of D 0.3 minus probability of B and D, which we just now calculated in part A. Again, please check out my YouTube video link. Okay. Contingency tables. A contingency table provides a way of portraying data that can facilitate calculating probabilities. The table helps in determining conditional probabilities quite easily. The table displays sample values in relation to two different variables that may be dependent or contingent on one another. Table 3.3 shows the number of athletes who stretched before exercising and how many had injuries within the past year. What is probability that the athlete stretches before exercising? Stretches before exercising is 350 out of total of 800. And what is the probability athlete stretches before exercising provided or given no injury in the last year? So what is the total of no injury? 514, out of which how many were stretching? So 295 out of 514 is the answer to part B. Why, you ask? Because first in no injury last year happened first. So that total is 514, which is the total of the second column. And on the numerator for that will be the amount, the number of people who stretches, which is 295. So it is 295 out of 514. Table 3.6 shows a random sample of 200 cyclists and the routes they prefer. Let M is equal to males and H is equal to hilly path. Okay. Out of the males, what is the probability that the cyclist prefers a hilly path? So males happen first and then hilly path. So total of males is 90. Out of them, how many hilly path? So the answer to part A is 52 out of 90. Are the events being male and hilly path independent? The total of males is 90 out of 200. So 90 out of 200 is not equal to 52 out of 90. Okay. Hence, the hilly path and males are not independent. Again, please check out my YouTube video link, which I'll post. Okay. And then we have tree diagrams. Okay, a tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. Tree diagrams can make some probability problems easier to visualize and solve. In an urn, there are 3 red balls and 8 red balls. So you see there in a there are 3 red balls and three the 3 balls are red and 8 balls are blue. Draw 2 balls in at one at a time with replacement. With replacement means that you put the first ball block back in the urn before you select the second ball. A 10 tree diagram using frequencies that show the possible outcome follows. Okay. So you can see from the top comes 2 branches with 8B. 8B means 8 blue balls and 3R means 3 red balls. Okay. Using the frequencies. The first set of branches represents the first row. The second set of branches represent the second row. Okay. So 8 blue ball and 3 red ball. Okay. So you can, next you are drawing a ball from those that urn. You can have 8 ball and 3 red. Okay. The other outcomes are similar. Okay. So each of the outcomes is distinct. In fact, you can list each red ball as R1, R2, and R3, and each blue ball as B1, B2, B3, B4, B5, B6, B7, and B8. Then 9 RR outcomes can be written as like this: R1, 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 R2. Okay. R1, R3, R2, R1, and then R2, R2, okay, and R2, R3, R3, R1, R3, R2, R2, R3. The other outcomes are similar. There are a total of 11 balls in the urn. Draw two balls, one at a time, with replacement. There are 11 times 11, 121 outcomes. The size of the sample space is QR total 64 plus 24 plus 24 plus 9 equal to 121. So total is 121 outcomes. Red and red. That means both the draw are red. Okay. And RR, you can see it is 9. 9 R and R out of 121. 9, 121. RB or BR. RB can be 88, 24, or BR can be 24. So 24 plus 24, 48 out of 121, and so forth. Okay. And then go into this. Venn diagram is a picture that represents the outcome of an experiment. It generally consists of a box that represents the sample space S together with circles or ovals. The circles or oval represent events. So this is a Venn diagram. Suppose an experiment has the outcomes 1, 2, 3, dash, dash, 12, where each outcome has an equal chance of occurring. Let A be 1, 2, 3, 4, 5, 6 as shown in the diagram, and B 6, 7, 8, 9. A and B where both occur is 6. And A or B will be 1, 2, 3, 4, 5, 7, 8, 9 plus 6. We do not list 6 twice. So it's 1, 2, 3, 4, 5, 6, and then 7, 8, 9. Although 6 occurs in both A and B, 6 is listed only once. Okay. 40% of the students at a local college belong to a club and 50% work part-time. 5% of the students work part-time and belong to a club. Draw a Venn diagram. Okay. Showing the relationship. Let C is equal to student belongs to a club. So club is 40, 0.4. And work part-time is 0.5. Okay. So 40 and 5. Okay. The first circle area on the left is 0.4. The second circle area on the right is 0.5. What is the common area? Is 0.05, where they belong to a club and work part-time. Okay. So I stop here today. If you have any question or comment, write me a note. I will also post my the links to my YouTube videos where I worked out the sample problem. Please check those out. If you have any question or comment, do not hesitate to write me a note. I'll get back to you as soon as I can. And if you like this video, share with your friends. If you like this video, please give me a thumbs up. If you like this video, you and your friends, please subscribe to my channel, Math Science Topia, by hitting the red subscribe button at the bottom right corner. And do not forget to check out my channel next time when I'll be back with another interesting problem, interesting solution. Thanks for watching. Take care. Have a nice day. See you next time.